Hi, I'm Tapio Kramer from Incron. In Part 1 I introduced you to the event chains that provide new perspectives and insights into the dynamic behavior of complex automotive electronics. At the end you might have thought, okay, nice, but how can I get these event chains when my fragments are developed by other parties? How can I compile all required data to the model then? In Part 2, I will introduce you to a methodic approach how the collaboration among all the teams will achieve this, a joint understanding for the dynamic behavior end-to-end. Starting point is a model-based approach for three good reasons. The OEM can model and analyze the end-to-end event chain before the system has been built and integrated. And the ECU developer can derive the robust and reliable architecture in the system and the software design phase. Secondly, through abstraction, we get rid of the complexity of all the details. We really focus on the timing. And third, design alternatives can be evaluated and compared very fast in short iterations, sometimes within minutes. Unthinkable if you would have to implement, integrate, and test them using real hardware. In the model, we have abstract resources for every resource, like CPU or bus. The scheduling of tasks can be imported from AutoSAR configurations, for example. Now, what do we do with this timing model? We call them task models, by the way, without real-time requirements. The requirements properties regarding timing and performance are compiled using real-time datasheets. They list the classic requirements like CPU and bus load and response times. For event chains, more detailed requirements can be defined and tested, like latency, data loss, or unwanted reuse of old data. Using the Incron tools, these requirements are checked. The system will be optimized using what-if analysis until all the requirements are met. In the early design phase, the OEM defines the real-time requirements of his functions, of his software components in real-time datasheets. He checks and refines the requirements and the mapping of the function blocks onto the ECUs until all requirements are met. These validated requirements become part of the specification for the suppliers. Every supplier then writes his own datasheets and timing models for his subsystem and performs his own validation. They then are passed to the integrator. The integrator checks if the overall requirements are met too by performing a virtual integration of the subsystems. Now, the important question is, isn't all this modeling quite time-consuming and complex? Here we see the initial effort in man-hours we have to model typical systems in various automotive domains. A body controller takes round about 5 man-days. A more complex driver assistance system takes up to 25 man-days to model. And that includes modeling the critical event chains too. The effort to perform these what-if analysis I'd like to show you on the next slide. Often one will experience that a local optimization will lead to a degradation, a violation of other requirements in another part of the system. That is why it is so important to understand the root causes for real-time errors. And you have to be able to evaluate these alternatives fast. That will not only save time, but also nerves and money as well. The impact of changed task priorities or synchronized clocks can be observed within minutes using these models. Changing the mapping of functions to CPUs or evaluating different task structures is done within a few hours. Certainly, there are other optimizations that will take a bit more time, but that's included in these numbers. There is a significant observation when we work with our customers. Once there is a possibility to see, understand, and describe the timing effects, more requirements are defined and detailed. That helps to find and avoid errors much more early. From the time when we come to the project and discuss the situation until we've done our job, there is an increase by 75% of real-time requirements. The awareness and ability to define the timing and performance needs grows. And that, in the end, will reduce the risk to find complex errors late or never. There are some more numbers we've extracted from our work that hopefully will give you an estimate where the largest risks are, where most real-time errors are. Most prominent are the classical real-time errors. A task is too late, or a maximum CPU or bus load is exceeded. Event chains errors are often as well, but in contrast to exceeded loads, there is no safety margin or exception allowed. Event chains have to complete in time. Another observation is that the load and response time requirements for tasks had been introduced to safeguard the end-to-end function. The details haven't been thought of, but they don't suffice. Event chains can fail even though the load and response time requirements along the event chains were all met. So, how important do our customers rank these event chains? Meanwhile, modeling and evaluating the event chain has become standard in most of the projects where we were involved in. Why? Because of the increased integration and networking of functions in these systems. What are the causes for the event chain errors? It is not only drifting clocks or bad mapping of software components to the ECUs. They mainly fail because precise, detailed requirement definition is missing. What in detail is included in the 250 millisecond requirement from the OEM for the event chain? The asynchronous sensor as well? Until the CAN task sent was activated? Until the message was written into the send register? Or until the last bit of the message was on the bus? Until now, the developers couldn't observe the dynamic behavior of event chains. So why should they define it in detail? The causes for event chain errors within the ECUs are similar. When is a signal detected at first occurrence, or when the plausibility check has completed? May a single sensor read be lost? What if oversampling is included? The Tier 2 assumes the integrator will take care of the data integrity. Does he also define it as a requirement when integrating his function? Now, where did most of the problems occur? From the OEM perspective, not in the subsystems. They worked as specified. But even if the subsystems work properly, will the integrated system work as well? A similar situation is observed by the ECU supplier or the integrator. Once event chains cross software components and include runnables from different development teams or Tier 2 suppliers, you have to go into details and analyze the end-to-end behavior as well. You have to zoom in and zoom out. That's the key. Mr. Augustin from Audi, one of the co-authors of this presentation, presented at our real-time Congress his experience with our solutions. The task? 3 into 1. Functions from 3 different ECUs had to be integrated into one new ECU, with some obstacles. The former Tier 1 suppliers became Tier 2s, and had to collaborate with their competitors. And Audi themselves provided some functions as well. The methods I've presented were used in this project with success, but a bit late when the implementation phase was 60% completed. Not too much details about the project, but there were event chain problems when we were introduced to the project. But no one knew that. This successful project led to the conclusion that in the new project the real-time methods and tools are used from the bidding phase on. Take a look at his presentation, available to download on our homepage. In Mr. Augustin's project, we also performed very expressive sensitivity analysis. By step increasing, for example, the net execution times of the software, one can easily observe the robustness of the system. Will minimal exceeding of an execution time budget lead to a disaster? Or is the system robust as in design C? Quite interesting from the quality assurance perspective is the presentation from Dr. Fuchs from Continental. He presented how the predicted feature ramp up and its resulting error curve differ from the real ramp up and error curves. He demonstrated how one can calculate if the team will be able to eliminate all errors in time of their system with the given tools and competencies. That was actually a quite sobering industry example. His conclusion is, there is no way other than a model-based development to be able to lower the error input and absolute amount of errors. His curves show all error types, including the real-time errors. For real-time errors, it's not the total number of errors that count. Often, a single real-time error is already a showstopper. For example, what if the redundant calculation for an ASLC function calculates with data of different age because of the clock drift between function calculation and redundant calculation? What if the estimated performance reserves are not sufficient to implement a late change request? That's why it's so important to minimize the risk of real-time errors by moving them from integration phase to the early design phase. Many successful series projects have shown that this is possible. Believe me, besides the event chain diagrams, there are way more perspectives to your dynamic systems behavior than I could present in this short video. Real-time errors are often found late, but have their origins in the early design and requirements phase. When using the presented methodology, you as a functions developer can ensure all your timing and performance requirements will have been incorporated before the bad awakening during the integration phase. As an architect, you will have fun to derive and validate an architecture that has the required robustness and performance. The project leader can monitor the status of the real-time and performance requirements throughout the project, not just hope for the best until late in the integration phase. And you as the manager will want the project to complete in time with a high probability of success and profitability, which is a challenging task in today's complex development projects. With this, I'd like to thank you for watching these presentations. If you have any questions or comments, please don't hesitate to contact us. Thanks.